So let's talk a little bit about gene mapping and identification. So remember that these two things can be utilized to allow or permit for more effective treatment of genetic diseases. And this is the whole purpose of genetic mapping and identification. Because essentially what you're doing is you're mapping mutations that happen in specific loci on specific chromosomes. So you kind of know the exact position of this mutation, and this allows for better treatment or enhanced treatment. And so you have two types of mappings. You have physical mapping, so this provides exact physical distance between the genes located on a chromosome. And this can be utilized, of course, to find out the physical location of a disease-causing mutations on chromosomes. And this is ideally measured in nucleotide basis. Then genetic linkage is a little bit different. This is the arrangement of genes and genetic markers on a chromosome. Okay, so this has got nothing to do necessarily with nucleotide basis, at least directly. What you're looking at is the position of these genes on the chromosome and the genetic markers on the chromosome. And this is calculated using something called recombinant frequency. So let's look a little bit about that. Well, let's first observe the picture here to the right. Well, here we have two loci on a chromosome, right? If the distance is big between the two, it is very likely that recombination will happen between the two loci. But the alleles will most often not get inherited together. If you look at here, to the right, if it's a little distance between the two loci, it is unlikely for recombination to happen, and the alleles will get inherited together. So this is linkage, right? Linkage meaning that these loci or genes are linked together. So when they get inherited, they are linked together when they get inherited. And of course you have a couple of terms. You have complete linkage, you have incomplete linkage, you have independent assortment of these things. And I'm assuming you already know this stuff. But to put it lightly, the distance between two loci is measured in something we call centimorgans. And centimorgans, basically 1 centimorgan means the recombination frequency of 1%. Now what is recombination frequency? Well, the distance between two loci, for example A and B here, can be found by looking at how often recombination happen in families. And so how often recombinations happen in families, that is what is called recombination frequency. And 1 centimorgan means a recombination frequency of 1%. And actually, you can kind of convert this to the physical map, because 1 centimorgan is around 1 million base pairs. However, this number varies quite a lot in different contexts, and I'm not gonna go through it all here, but to put it very lightly and roughly said, 1 centimorgan is approximately 1 million base pairs. Just remember that this does not apply to all cases. And so the two loci on a specific chromosome could either be a marker locus and a marker locus, and marker locus and disease locus. So of course the disease locus is the locus related to that disease, but what is a marker locus? And a marker locus is something that we have utilized to kind of make all this genetic mapping much easier for us. So polymorphisms that are used to follow a disease-causing allele through a family are what is called markers. And they can mark the chromosome on which a disease-causing allele is located. So basically, this is just a genetic variation on a locus, okay? A locis. So we also say that if the genetic distance is 0 centimorgans, it indicates no recombination, implying that the loci are completely linked. They're completely linked. Now suppose that we have a 50 centimorgans apart, the two loci. We then actually say that the loci are called synthetic loci. The loci are under the same chromosome, but they're unlinked. And this is equivalent to independent transmission, as in the case of alleles of loci that are on different chromosomes. So although they are on the same chromosome, these loci are on the same chromosome, but if the distance is 50 centimorgans apart or more, actually in fact it cannot be more, because that is the maximum. But if it is 50 centimorgans apart, the distance between two loci are then called unlinked. Okay, so this is the equivalent of loci being at two different chromosomes. Now let's try and do this task here. So in the following family, a monogenic disease is inherited. In the first intron of the disease gene, there is a marker locus with the alleles A and B. The genotypes with respect to the marker locus are indicated for generation 2, generation 3, 2, and generation 3, 3 in the pedigree. So, as you see here, you have the genotypes with respect to the locus marker here. And now they ask you, are the available data sufficient to determine which allele A or B is a disease-linked allele, and justify your answer? And here the data is not sufficient to determine which allele A or B is disease-linked allele, because we cannot deduce whether or not allele A or B is a disease-linked allele at generation 3-2 here. So both A and B can be inherited from the healthy mother in generation 2-2 here. And the genotype of this father is unknown. So we don't have sufficient data to be able to determine this. Now they ask you, let's assume that in generation 2-1 here, so this father here, had the genotype capital B, capital B. What genotype would you now expect to find in the fetus, IV1 here, so in generation 4-1, if it has received the disease allele? Now suppose this person has received the disease allele, and we know this father's genotype. We're no longer talking about so his genotype is capital B, capital B. So either way, he will give one capital B to this guy. Okay, he will give one capital B to this guy. Even this actually indicates autosomal dominant, but that's not really what they're asking about. But this person will give a capital B to this guy right here. And so we know he has the disease allele. So the disease allele could only be capital B. So this guy has definitely received capital B. And this mother, she has two capital B's here in her genotype. So she will, it will only, like, the only possible thing here is that this person will have the genotype capital B, and he will have the disease allele from this father. Okay, so that is the genotype we would expect to find in fetus in generation 4-1 here, if he has received the disease allele from this father.